Okay, yes. Quentin Dubroff on the Erd H distinct subset sums problem. Please.
Yeah, so thank you very much for the invitation. It's nice to be here. Okay, yeah, I guess I should say I'm from Rutgers. I'm graduating and going to Carnegie Mellon next year. Okay, so that's out of the way. Okay, so what I'm going to be talking about is this property of a set of integers. So here we're fixing some set of integers, and you're free to think of them as positive. It really won't matter. And the property is having distinct subset sums. And what this means is a subset sum is you fix some subset I of the first n of the indices. So n is my notation for the first n integers. So I fix some subset of n, and I sum up all of the elements with indices in I. So that's what a subset sum is. And the distinct part of subset sums is saying that there are every one of these subset sums is distinct. Okay, so yeah, so in other words, there are 2 to the n subsets, and all of those are distinct. Okay, so for example, you can look at the powers.
Allowing for the empty set whose sum is 0, right?
Yeah, we're allowing for the empty set. Yeah, not a big deal if you don't want to think about that, but yeah, we'll allow it just to have, mostly so I don't have to write -1 or anything like that. It doesn't really matter, but thank you, yeah. Okay, so the first example, when you're thinking about this, is the powers of 2. So here, every integer has a unique representation in base 2. So that immediately tells you that's equivalent to the fact that the powers of 2 have distinct subset sums. And in a sense, the subset sums are pretty well packed in. The subset sums are exactly the integers from 0 up to 2 to the n minus 1. Okay, so it's a very well packed set of subset sums. And the largest element grows like a power of 2. So this is what Erd H was getting at back in the 30s. So today we're going to be studying this conjecture of Erd H, which it really asks how well packed can a set of integers be if they have distinct subset sums. Okay, so again, you really can just focus on the case where the AI are all positive, and just for convenience for the rest of the lecture, we're going to be thinking that the AI are ordered naturally like this. So you can just fix some indexing where they're ordered like this. And Erd H conjectured that really the powers of 2 are in some way extremal, meaning that if you have this set of integers with distinct subset sums, then the largest element really needs to grow. It really needs to be close to 2 to the n. So some constant times 2 to the n. And this, I don't know, this is somewhat innocuous conjecture. It's made by Erd H in the 1930s, and actually apparently this was made in like 1931 or 1932. And I just looked up on Wikipedia that Erd H was born in 1913. So Erd H is a teenager at the time of making this conjecture. It's a pretty innocuous packing problem, but it turns out to be extremely difficult. So I'm hoping to say a bit about the difficulty as we move forward today. Okay, questions about the statement of the conjecture? Okay. Okay, so
do you have any numerical evidence? In other words, has anyone looked, at the first million integers or whatever, and has anyone looked at anything and come up with some statistics?
I'll talk about that in the next slide. Yeah, okay. Good question. But we'll see that numerical evidence is hard to come by. Okay, so I just want to say first that 2 to the n is the right scaling, or in other words, there's an easy argument showing that the largest number has to be at least 2 to the n divided by n. And to see this, you note that, well, the maximum size of a subset sum is n times an. So this tells you that all the subset sums lie between 0 and n times an. I mean, the -1, all these things are not important. But we have all the subset sums are between 0 and n times an. So there's 2 to the n distinct integers lying in this interval. So you immediately get that n times an is bigger than 2 to the n. And rearranging gives this result. And focusing on this strict equality, you can improve this bound a little bit. So I'll leave that as an exercise. But really, for this rough estimate here, I just want to focus on the order that we already know that the largest number needs to be at least 2 to the n over n. So 2 to the n is the right scaling, and we're really worried about this lower order term. So can you remove this dependence on n? Okay, so if you start studying this, and you might want to just think about what type of constructions do we get. And okay, so you can actually improve upon powers of 2 already pretty quickly. So what we're looking at here in the table, AI is going to be really the best value that you can put on the right-hand side in this conjecture of Erd H for a fixed n. So for example, if we're allowing 3 A1, A2, and A3, then you can fix the first 3 powers of 2 here. So this gives you a subset sum distinct set with largest element equal to 4. But now notice if we allow 4 elements in the set, well, you could do the set 1, 2, 4, 8, the powers of 2. But quickly, you notice you can do a little bit better already. So if you calculate this out, the subset sums of this set are already distinct, and you get some improvement over the powers of 2. Okay, and continuing on, as the number of elements in your sequence gets larger and larger, we notice you continue to get a little bit more improvement over the powers of 2. So 13 is now already a good bit smaller than 16, and 24 is a good bit smaller than 32. And already here we're comparing 161 with 256. So this is, a good bit smaller, constant fraction smaller. So really we can get some decent improvement. It turns out all of the examples except for, this example for A3, these are things coming from the Conway-Guy sequence. So Erd H's conjecture was studied by Conway and Guy, and they define they have some recursively defined sequence from which you can start finding these sequences with distinct subset sums. And they're in the limit of their sequence. The best constant you can do is already significantly smaller than the powers of 2. So the powers of 2 an is 1/2 times 2 to the n, and here you're getting something already smaller than 1/4 times 2 to the n. And Conway and Guy actually conjectured that the examples coming from their sequence were optimal, meaning the best packed sequence of a set of integers with distinct subset sums. And this actually ends up not being the case. So Tom Bowman, who is actually my academic brother, in his maybe right after his PhD and his postdoc, found examples where an is already a bit smaller than the examples coming from the Conway-Guy sequence. Okay, so the point when you're constructing all these is, it's very difficult to prove that a given sequence has distinct subset sums. And the point here is that the number of subset sums is exponential, and lurking in the background of this problem is something called number balancing. Okay, so this is some NP-complete problem in computer science, and really it's asking, it's the decision problem, does a given set of integers have distinct subset sums? So that's sort of an instance of this number balancing problem. And this is one of the fundamental NP-complete problems. Okay, so there's some like significant things lurking in the background here for why it's difficult to work with these things. So whenever you think of a rule for defining these, for defining a sequence with distinct subset sums, this rule needs to really be pretty powerful in helping you decide if the sequence indeed does have distinct subset sums. Okay, and then, yeah, so also these are equalities here. So these are literally the best values in Erd H's problem. And so the fact that they exist comes from the Conway-Guy sequence. The fact that they have distinct subset sums comes from that analysis. But the fact that it's optimal comes from a computer search by Fred Lunnan and some others. And actually, when I was giving this talk or a previous talk, Neil Sloan from the OEIS wrote to me and asked me if I knew anything else about the problem, and pointed out that A10 is actually unknown. So I think that would actually be really nice to continue on finding these AIs, but this really is computationally hard. So Neil wrote to Fred and asked, is A10 within reach? And Fred wrote that in 1988, the computation here for A of 8 took about 20 hours, given a pretty complicated computer program. And A9 apparently was estimated to take about 18 months. So A10 does seem pretty difficult, but I think, the advances in computation since then maybe outweigh how long this increase in complexity, but probably A10 would be a pretty interesting thing to calculate here. And really, I mean, extrapolating from data, maybe A10 is within reach, but A11 is impossible. So extrapolating from data is maybe hopeless for this problem. But it would be really nice. Because, yeah, our progress on beating anything from here it seems to be very difficult. So any improvement on Tom's bound here would be really nice. Okay,
Just
so
out of
yeah.
curiosity, what were those constants that we were looking at a second ago? The
This,
point, yeah.
This is the Conway-Guy sequence, and the sequences that Tom gives are some recursively defined sequence, and you solve the recurrence and you find the asymptotic there. I don't have any great insight onto what those are. Yeah, sorry. I can point you to the papers.
I mean, it's not like you can know. It's not like they're algebraic or something.
Right. Yeah. Not at all. I mean, perhaps these things fall out from. Yeah. I really don't know. I mean, I never tried to put in one of those symbolic calculators that tries to tell you what a particular constant might be, but I would be surprised if it had something, some, interpretable meaning. And really, I would also be surprised if that was the constant coming from these examples was optimal. I think that would be already surprising too. So I don't know if that's exactly, I would be surprised if that told us anything, in other words. But yeah, thanks. Okay, so those are the upper bounds. And actually, and when I say upper bounds, I mean, we're looking at the best possible sequence of A1 through AN. And yeah, one last thing while I'm still talking about upper bounds. All of these things come from explicit construction. So the Conway-Guy sequence is explicit, Bowman's example is explicit. Everything else that we know about is some explicit construction of a set with distinct subset sums. So maybe there's some way you can improve on these things without giving an actual set. Okay, so the lower bound is the lower bounds that we know are all of the form 2 to the n over square root of n. And this has been known since the 60s. And really all of the improvement, there's been a long history where people have worked on this, and the improvement has really only come in the constant factor out in front. Okay, so again, the conjecture is that we can remove this square root of n factor. And all of the constructions we know are without this square root of n factor. Yeah, it seems wide open to decide if the actual truth is closer to square root of n, or if the actual truth is Erd H's conjecture, or somewhere in between. Okay, so the first example of this bound 2 to the n over square root of n is Erd H and Moser from the 60s, and they're using a second moment type algorithm, or a second moment type argument. Yeah, I don't exactly know some of the details super well, but Alon and Spencer, I think, optimized this second moment algorithm, second moment method, to get this improved constant. Okay, and now the next improvement comes from a nice argument of Elke's, which we might see later today, which says that actually this C can be taken to be 1 over square root of pi. And this is a really nice, like, sort of Fourier analytic argument. Yeah, and it's really pretty, and also seems maybe like a good thing for future improvement. So hopefully we'll get time to see that. And then really shaving just a very small amount off the constant is 2 papers of Bay and then Guy, I think independently though. And really what they do is they're analyzing the variance in a way that's not exactly second moment, but it's somewhere close. So you get some small improvement here. And this will form the basis for some of our future improvements. And then the last 2 things in the history are a paper of Iskender Aliyev, and he achieves this constant square root of 3 over 2 pi. And this is really nice. It's using geometry of numbers, and you know, talks about the connection of Diophantine approximation, things like this. So it's really pretty argument. And I ended up finding, while working on this, I found sort of maybe a primitive version of the argument from Aliyev, and it's very simple. So I'll present that hopefully later today as well. And finally, the last improvement is this factor of square root of 2 over pi. So this was noted by Elkes and Gleason, and I don't know how they proved it because it was unpublished. So I didn't know about it, and with Jacob Fox and his student Max Wensheng Zhu, we found the constant square root of 2 over pi. And we did 2 separate proofs. I found a proof and they found a proof really at the same time, and we chatted and decided to have a joint paper, which was really nice. They sort of let me onto their paper, which was very nice of them. But yeah, so I'll be talking about the 2 proofs of this first. And yeah, hopefully we'll see that this square root of 2 over pi result is somehow square root of 2 over pi is like the best you can expect with really any of the methods from this whole list. So I mean, at least Jacob, Max, and I, we really think that any improvement square root of 2 over pi plus, you know, plus some epsilon would already be really good. So I'll just record that here. Plus epsilon would be really nice already, because that somehow, it seems like achieving anything like this would require you to use some type of arithmetic information that we're sort of ignoring in our approaches. So that would be quite nice. All right. Okay, so moving on to the proofs. So the first thing, I think maybe some people know this, but at least they know the second moment argument, but maybe they haven't seen this specific one. I'm presenting it because we'll actually need it in the first proof of our square root of 2 over pi result. So this is the result of Erd H and Moser's. Oh, yeah, my history is off. I don't know. I couldn't actually find the exact publication record, so I think I maybe equivocated a little bit. But yeah, so what we're going to prove is that the largest size, the largest integer in a set of integers with distinct subset sums is at least 2 to the n over square root of 3 over n. And it's a probabilistic argument. What we do is you fix random variables epsilon through epsilon n, and you want them independent, uniform from plus and minus 1. So they're coin flips. And the insight is to form this random variable x, which is just this linear form over the AIs. Okay, so you form this random variable, and you can immediately calculate the second moment of x using the fact that these epsilon I are independent and uniform. We get the expectation of x squared is exactly the sum of the AI squareds. So of course this is at most n times the maximum value of AI squared. But the insight here is now we can actually calculate this expectation of x squared in a different way. So what we notice is that x has a very particular form. So here's the number line. Here's 0. And what I'm going to do is I'll draw filled in here are the points in the support of x. And the insight is first, well, x doesn't take the value 0. So if x took the value 0, then that would correspond to some terms with epsilon I positive and some terms with epsilon I negative, summing to 0, which you could just very quickly rearrange to find two subset sums which were equal to each other. So first of all, x is non-zero. Secondly, every value in x takes the same parity. So when you switch some epsilon I from +1 to -1 or from -1 to +1, the value of x changes by 2 times AI. So it changes by an integer, an even integer value. So this immediately tells us that x always takes the same parity, and it only takes a given value one time. So this comes from the distinct subset sum property. So in other words, the support of x looks something like this. So here's -1, 1, 2, 3, and so on. So this is what the support of x looks like. And we can calculate the variance just in the naive way. You look at every possible value in the support of x, and you just sum the distance from 0 squared. Okay, so each of these possible elements in the support happens with probability 1 over 2 to the n. Okay, so you can write down a formula for the expectation of x squared just by looking at the support. And the point is that this expectation of x squared will be smallest when x exactly looks like all odd integers. Okay, so you can do a shifting argument. If any, and the thing that I'm not going to prove is that if x is uniform over 2 to the n non-zero integers of the same parity, then the smallest value of the expectation of x squared happens when, well, I'll write it up here. The support of x is equal to, well, -1, 1, -3, 3, -5, 5, and so on. Okay, so this is the extreme case for the support of x. And even in this extreme case, the smallest possible value of the expectation of x squared is, well, you just you calculate out the sum of all these expectations, and it turns out, you can just write down the exact expression for this sum. So what we found is that the expectation of x squared is always at least 4 to the n minus 1 over 3. But it's always at most n times an squared. So you compare this lower bound and the upper bound, and it immediately gives you your result by rearranging. Okay, so this is nice. We're already close to the best known constant with this very simple argument. And it also tells you something optimal, which is that the expectation of x squared is always at least 4 to the n, divided by 3, roughly. And again, this is achieved when the support of x is this, which is essentially what happens for the powers of 2. Okay, so this lower bound on the expectation of x squared is completely tight. And really all of the loss in this argument is coming from the fact that we're estimating the expectation of x squared by this lossy inequality, saying that the variance is at most n times the maximum element. Okay, and we're going to see this several times today, where we just keep losing some factor. We keep losing the square root of n factor because all of the arguments are somehow controlling the 2 norm of AI. Okay, so to improve on this result, we're going to use something called the Berry-Esseen theorem. So what we noticed from the last result, again, is that it was only tight if the variance is basically n times an squared. And in those cases, if expectation of x squared is approximately n times an squared, you really expect some type of central limit theorem to hold. You're kind of summing these IID random variables. Okay, so I'll just read this out to you. The Berry-Esseen theorem says if we have independent random variables.
Yeah, you didn't actually mean IID, you just meant ID, right?
Yes, sorry.
Identical, and they're not identical.
Right. So what I meant here is that if the expectation of x squared is really approximately n times an squared, then really they are almost identical. All of the AIs are roughly the same. But yeah, in Berry-Esseen theorem, I'm losing the identical. So yeah, for the actual proof, we are forgetting about identical. Okay, so we're going to analyze the same random variable from the Erd H proof. But first, for this theorem, we're looking at the sum of independent random variables, which are centered. So they have expectation 0. Sigma squared is the variance of the sum. And all we need is that we have some bounded third moment. Okay, so once you have bounded third moments and centered random variables like this, you start expecting a central limit theorem, and the Berry-Esseen theorem is giving you the quantitative estimate on the central limit theorem. So what it tells you is that if f of x is a cumulative distribution function of x, and psi of x is the distribution function of the centered normal with the same variance as x, then they're close exactly in this sense. So they're close in the sense that really the third moments shouldn't be too large compared to the second moments. Okay, and it turns out we'll be able to assume something like that in the proof. All right, so back to the Erd H proof. We're studying this random variable x, which is this sum of epsilon I ai, where I'll just remind you epsilon I is uniform in -1, 1. Okay, so we're calling from the last proof, x is uniform over 2 to the n integers, and again, they all have the same parity. So you can immediately see that the probability that x lies between minus L and L is at most L plus 1 times 2 to the minus n. So each of these integers happens with probability 2 to the minus n, and the same parity constraint forces this to be L plus 1 instead of something like 2L. Okay, so this gives you some upper bound on this probability, and what we're going to do is we're going to count it in a different way. We'll give a lower bound using the Berry-Esseen theorem. So to do this, we fix delta as 1 over log n, but really you just need something which is slowly tending to 0. And the first insight is that the Erd H proof is only tight. It was tight exactly where I told you here, where the expectation of x squared is really close to n times an squared. So in other words, if an is pretty somewhat small compared to the standard deviation, well, we already know exactly what the standard deviation squared is. It's 4 to the n minus 1 over 3. So if an is large compared to this, then you rearrange and you immediately get something like, this implies an is bigger than big omega 2 to the n over log n. Okay, so this is, you can see there's already a lot of room here. So I'm saying if an is big compared to the standard deviation, then we're just immediately done from the Erdős-Moser argument before, because we already know the standard deviation has to be kind of close to 2 to the n. Okay, but if an is small compared to the standard deviation, well, then you can actually calculate this sum of the third moments. The sum of the third moments is exactly the sum of the ai cubed. So pulling out the max term here, the sum of the ai cubes is at most an times the variance. And since an is small compared to the standard deviation, this is some small constant times delta cubed, or times sigma cubed. And again, so for the Berry-Esseen theorem, you're working exactly with the sum of rho I over sigma cubed. So this is going to translate into a small bound in the difference between these two cumulative distribution functions. Okay, so indeed, this is exactly what we get. What we're going to do is we're going to bound probability that the random variable is at most L via the Berry-Esseen theorem. And here now, I haven't told you what L is. So here, I'm going to fix some alpha as square root of delta. So it's going to 0, but not quite as fast as delta. And we're going to be studying the normal approximation when L is alpha times sigma. Okay, so L is pretty small compared to the standard deviation. So in the bell curve, we're really working quite close to the center, and we're looking at this probability here. This is the probability that x is at most L. Okay, so what Berry-Esseen tells us is that x is approximated well by a normal random variable up to this error term, which is delta. So we're calling, again, this is something like 1 over log n. And because L here is pretty small compared to sigma, we know that e to the minus x squared over 2 sigma squared is really close to 1. So, we're doing this integral right at the very peak of the bell curve, and we're doing it, for quite small width, and we're just saying the width of this rectangle is is roughly the base of it, which is 2L times the height, which is 1. And then there's this normalizing factor out in front. Okay, so that the expression becomes square root of 2 over pi times L over sigma. And using the fact that alpha is significantly bigger than delta, we can forget about this, this second term here. Okay, so now using Berry-Essien, we have some upper estimate on the probability. Sorry, we have some lower estimate on the probability that X is at most L. So comparing these two things here, we get exactly this fact that the upper bound here is roughly the lower bound. So I'm using this greater than or asymptotic to forget about lower order terms. So I'm going to be a bit sloppy with this throughout the lecture, but I hope that doesn't bother anyone. Please let me know if it does. Okay, so what you do is you rearrange this thing, and you immediately get that the standard deviation is at least 2 to the n times this factor square root of 2 over pi. And again, so now we have an even tighter bound on the standard deviation. And now you kind of use this lossy inequality, and we say, well, the standard deviation, or possibly lossy inequality, to say the standard deviation is at most square root of n times an. Okay, so this is our second proof, and it's this observation that somehow you can use normal approximation, and it's kind of funky because we're doing a normal approximation on this random variable x, and x takes discrete values uniformly. So we're approximating x, which really is x just looks like some peaks on the integers like this. This is a bad attempt at drawing what the PDF of x looks like, and somehow we're approximating it with the bell curve. So this is it's sort of a funky thing that we're doing here, but it's getting at the fact that the variance argument really it should be able to be tightened up a little bit whenever some like this inequality is close to tight. Okay, questions on this proof? All right. So the next proof is has some similarities, but is really using some different ideas. So I'm going to be now proving the same result. So I'm proving this bound 2 to the n over square root of n with this same constant, which is the best we know. But what we're going to use is now some isoparametric result of Harper. So what we're working in the hypercube. So we have a family of subsets in the hypercube. And given a family of subsets, its vertex boundary is the set of subsets which are not in the family, which are at distance 1 to the family, distance exactly 1 to the family. So where the distance is measured in the symmetric difference. So I'll just give you two examples here. If f is equal to n choose at most and the floor of n minus 1 over 2, then the boundary of f is exactly, oh, sorry, this is my notation for all subsets of n with size at most n minus 1 over 2. And if that's your family, then the boundary of f is exactly all subsets of n of size ceiling of n over 2. And the pictures here, sometimes we draw the hypercube like this. If this is your family f, then this level here is the boundary of f. Okay, so what Harper's isoparametric inequality says, this is a very particular case, but what it says is if f is exactly half of the hypercube, then the vertex boundary needs to be large. The vertex boundary is at least the size of a middle level. And this example here that I just talked about shows that Harper is completely tight. And just for a little bit more orientation with Harper, and actually to motivate some discussion later, I want to point out that Harper can be quite far from tight. So if F is the set of things where the element 1 is not an A, well, then this is what F is. And the vertex boundary is exactly the top half of the hypercube. So this is some other picture of the hypercube here. And now, in this case, for this specific F, it still does have measure a half, but now the vertex boundary is exactly the top half of the cube. So F is the bottom half, the vertex boundary is the top half, and that's much, much larger than n choose n over 2. So Harper can be far from tight, even for some compressed sets. Okay, so this interplay between when Harper is tight, when Harper is not tight, seems like an interesting thing for this next proof. Okay, so questions on Harper before we do the proof? Okay. All right, so what we're going to do here is we're going to switch perspective a little bit. We're going to write our integers as a vector, which should be denoted as bold A. And the perspective here is that if this is the hypercube 0, 1 to the n, and this is our vector A1, this is the two-dimensional picture. This is the vector A1, A2. The distinct subset sum condition corresponds to the fact that any hyperplane orthogonal to the vector A should only intersect the cube in exactly one point. So that's how we're going to encode the distinct subset sum condition. Or in other words, you look at A as a vector and you look at projections of the cube onto this vector. And these projections are exactly what the subset sums are. So in other words, I'm saying that any subset sum can be written as bold script A dotted with Z, where this is the standard inner product, and Z is some vector in 0, 1 to the n. Okay, and we're going to define a family in the hypercube. So 0, 1 to the n is another way of viewing the set 2 to the n. So this is really a family in the hypercube, and it will be all of these vectors such that the inner product with A is at most M, where M is sort of the average subset sum. And because M is the average subset sum, the set of vectors with dot product less than the average is exactly half of the vectors. And actually, you can, if you want, you can argue that there's no dot product with, which is exactly the average. But that's extremely unimportant, so I don't want to spend time on that. Okay, so the point is we're looking at all these vectors which are most half the average, which is half the cube. So in this picture, this is exactly the set of vectors below sort of the central hyperplane. Okay, so this is some family in the hypercube, and so you can apply Harper to it. So Harper tells us that the vertex boundary of this set is large. All right, so the vertex boundary of F is large. But the main insight is that if there's a vector in the vertex boundary, well, the dot product with A needs to be bigger than the average because the vertex boundary is the set of things not in the original set, but also the dot product must be at most M plus AN. And this is because if you're in the vertex boundary, it means you started from some vertex in the set, and you just switched one coordinate from 0 to 1, since you're in the vertex boundary. And so from switching the coordinate from 0 to 1, that means something in the boundary is equal to x plus EI, where x is in your family and EI is a standard basis vector. Okay, so rearranging this, we get that y dot A is equal to x plus EI dotted with A. Well, x dot A is at most m since x is in the family. And EI dot A is exactly AI. All right, so everything in the vertex boundary has a subset sum which lies in this particular interval. But there are a lot of elements in the vertex boundary. So we have n choose n over 2 subset sums which lie in this interval, and all of these are distinct integers. So this tells us that, well, the interval length, which is an, it should be at least n choose n over 2. And that completes the proof using Stirling's approximation. Okay, so this is, yeah, we immediately get the same bound from the Berry-Yassine proof, but now we don't need to break into cases into the structure of the AI. So this works for anything. And this exactly comes from when Harper is tight. So this is nice because Harper is tight exactly when the Berry-Yassine proof is tight. And this is kind of coming from the fact that when Berry-Yassine and all these variance arguments is tight, this is happening when all of the AIs are roughly the same. And when all of the AIs are roughly the same, X sort of looks like a binomial distribution, and the binomial distribution approaches a Gaussian. So this is why we're getting exactly the same constant square root of 2 over pi in both of these proofs. And this type of Gaussian approximation and normal approximation, it's somehow I want to say this is why the factor square root of 2 over pi is a limit of these techniques. It seems like, you know, just proving using concentration tools, you won't be able to do better than a concentration like this. So again, it seems like you need to use some arithmetic information to improve on that constant. Okay, so that's those are the two proofs achieving the best bound. So are there questions on this before I start showing you some, maybe one more proof, and then I'll do some discussion?
Good.
Okay. Okay, so the last thing I'm going to show you today is a proof using geometry of numbers. And okay, so the proof, I'm going to achieve 2 to the n over square root of n, but now I'm going to lose, it's a factor of 1/2 instead of square root of 2 over pi. So it's non-optimal, so that's part of why I didn't publish it. But the real reason I didn't publish it is because the paper of Aliev really is, I think of this result here, which I'm going to prove to you today, is sort of like a janky, you know, non-cleaned up version of the Aliev proof. So the Aliev paper is nice and pretty, so I'd encourage you to check it out. But even here, I think it's nice, and it shows some interesting connections, and maybe even leads to some sections where you might want to improve on it. So I think it's nice to see. Also, if anyone has seen something similar to this, I'd be really interested in hearing about it. But we're going to use two tools. So the first, and they're both well known. The first tool is Minkowski's first theorem on the geometry of numbers. Okay, so we're now working with essentially symmetric convex bodies in n dimensions. So you should be thinking of you know, some body like this, and it should be symmetric with respect to inverting the body. So if you go in one direction, it looks the same as if you go in the opposite direction. And of course, this is an n-dimensional picture. Okay, but what Minkowski proved is that if we have a centrally symmetric body in Rn and the Lebesgue measure of that body is at least 2 to the n, then C contains a non-zero lattice point. Okay, and this is completely tight if you look in 2 dimensions and you just take minus 1, 1. Yeah, sorry, if you look in n dimensions and you take minus 1, 1 to the n, well, this is an example of a convex set. We can approximate it with convex bodies where the measure is arbitrarily close to 2 to the n, but the only lattice point this convex body contains is the origin. Okay, and just for comparison with the other proofs, Minkowski's proof of this uses a really nice pigeonhole argument. And actually, I don't think there are any fast algorithms for finding the non-zero point of ZD if we're guaranteed that it exists. So this is another NP-hard problem, NP-complete problem. Although I don't want to go into the formalization of what that means for Minkowski's theorem. Okay, so there's some connection between the pigeonhole and this NP completeness and the NP completeness of the subset sum problem. And I even saw a paper which uses essentially what I'm doing here to do the reduction, to show that subset sum is somehow computationally as difficult as the Minkowski problem. Minkowski problem of finding a non-zero point given that it exists. So there's some nice formal similarities here, but that's pretty much all I know about that. Okay, so the second theorem is a result of Wahler, and it studies central hyperplane slices of the cube. And what it says is the minimum central hyperplane slice, so the minimum n-1 dimensional volume is at least 2 to the n-1, which is achieved on half spaces. Or sorry, it's achieved when the hyperplane is orthogonal to a basis direction. So here's our n-dimensional hypercube, minus 1, 1 to the n, and this is a hyperplane slice. And Wahler's theorem says that the n-dimensional volume, n-1 dimensional volume of this hyperplane slice is at least the n-1 dimensional volume of one of these standard slices. Okay, so Wahler's theorem is maybe intuitive if you feel comfortable with visualizing things in n dimensions. Yeah, so how do these things work together to give proof of subset sums? Well, what we're going to do is we need to define some convex body, and we define this body of it's all points in Rn in this open set. So again, I'm going to be a little sloppy with approximations here, but if you want, you can do -2 minus epsilon and 2 minus epsilon and let epsilon tend to 0, but let's ignore that for now. But the main point is the body is defined by all points which have inner product with A at most 1. And the point of this definition is that C can't contain an integer vector. So what happens if C contains an integer vector? Well, all of the integers would need to come from -1, 0, and 1 because of the definition. Okay, so if you have something like this, which has dot product at most 1 with A, then you get something like sum of AI for I and I minus sum of AI for I and J is at most 1. But both of these things are integers, which means that they're actually equal. So that would give you 2 subset sums which are equal. All right, so C can't contain an integer vector, and Minkowski's theorem immediately tells us that the measure of C is at most 2 to the n. But on the other hand, we can use Waller's theorem to lower bound the estimate, or to lower bound the volume of C. And the point here is, I'm throwing away I'm ignoring some approximation terms, but this is the hyperplane x dot A equals 0. And what the convex body looks like is this small strip close to 0. And the width of the strip, okay, so Waller's theorem is telling us that the base of the strip has measure about 4 to the n minus 1, since now we're scaling everything by a factor of 2. And the half width of the strip is exactly 1 over the 2 norm of A. So this length right here is about 1 over the 2 norm of A. So ignoring things close to the edge of the cube, which you can do, we find that the volume of C is exactly this expression. And now we'll use the same inequality we've been using all day, which is that the 2 norm is at most square root of n times an. And comparing it with the upper bound coming from Minkowski's theorem, you rearrange and you exactly get the result we wanted to prove. Okay, so yeah, somehow there's this nice connection between geometry of numbers and the subset sum problem, but yeah, I think it would be interesting to know more about that. But I'd be really happy if someone has seen this theorem or seen this proof before, or anything really related. Okay, so there's one more proof, which I don't think we have time for today, but it's using generating functions. So the idea is to study this generating function. But I don't think we have time for this today. But it's a really nice proof. And this last Elke's proof, it turns out you can actually do a tighter analysis and achieve the best constant square root of 2 over pi. So this is a very recent paper of Steinerberger. Okay, and Elke's proof is in some sense a Fourier analytic argument, and I've been told the language for Steinerberger's proof is he's analyzing some other major arcs in the Fourier analytic proof, but I don't know this language very well. Okay, but the interesting thing here is that this argument, which I didn't show you, is tight. The isoperimetry and the Berry-Yassine theorem are tight when A looks like the all ones vector. And Elke's argument seems like there should be improvement. So maybe there's some improvement there. Okay, so the last thing I want to say is there are a lot of these variants, which, it seems like the problem is hard. So maybe we want to find a counterexample, but we need to relax the problem. So, Steinerberger asks, what if instead of all subset sums are distinct, what if we know that most subset sums are distinct? Or Bay asked, instead of looking for sums where the values take on 0, 1, what if you allow the values to take on 0, 1 through k? And a lot of the proofs go through and there's still the same gaps. But it seems like Erd H's conjecture could be generalized in that respect. Yeah, and then lastly, maybe we only look for subset sums where we restrict what the subsets look like. So for example, if you only look at subset sums in the middle level, can you still show like an is bigger than 2 to the n over 100 or something like that? Or maybe in this case, because there are fewer subset sums, square root of n bound is really tight. But now all we know is 2 to the n over n. And this is a problem of Balog. And similarly, this group, Costa, Delay, and Della Fiore, studied subset sums for this other restricted case, and they applied known techniques, and really doing anything beyond the known techniques would be really interesting. Okay, so thank you very much. Sorry to go so quickly through that last slide, but I wanted to finish on time.
Thank you. Are there any questions for
Thank you.
Quentin?
Very nice.
So having better estimates for the Erd H subset sum problem, does that shed light on any other combinatorial number theory questions?
I'm not really sure how it, I don't know any question it would actually affect. I know that in computer science, there are hard and easy instances of cryptographic systems that are based on subset sums based on how large AN is compared to 2 to the n. So I think it's loosely related, but I think this very precise control is maybe just a problem for its own sake.
Can you give an idea how Waller's proof goes? I mean, that theorem.
I have only skimmed Waller's proof. So I do not remember. It's been quite a long time. I'm sorry.
And what about this isoperimetric inequality?
So yeah, there are several proofs for Harper. So you can do some induction on N. So Harper it's nice in the sense that you can write down exactly what the minimum, what the best isoperimetric set is. And it turns out the best isoperimetric set is the first, the initial segment of the lexicographic order on the hypercube. And this holds for not just families of size half the hypercube, but any fixed size family. And this stronger statement allows you to do an induction. So what you can do is, you split the cube into 2 parts, and in the bottom part, you replace whatever the family was with this this initial segment, and the same thing on the top. And now you can analyze, and because these families are nested, you're able to, the analysis is easy, and the proof goes through pretty easily. Yeah.
Thank you. Thank you.
Other questions or comments? If not, thank you again, Quentin, for a lovely talk.
Yes, indeed. Thank you.
Good luck in Pittsburgh.
Thank you.
Can you close your screen share?